Hello everyone, my name is Keyang Yu. I am a PhD student from Cyber-Physical Systems Laboratory, Florida International University. It is a great honor to share our recent work, PrivacyGuard, enhancing smart home user privacy. This is a joint work with my lab mate Qi, my advisor Dr. Chen, and the other collaborators. As you may already notice that IoT devices has been expanding recently. For example, from this graph, which the x-axis is the year and the y-axis is the number of connected IoT devices in billions, it is projected that by 2025, there will be over 75 billions of IoT devices connected to the internet, and many of these IoT devices are deployed in smart homes. Here are some examples including voice assistants, smart meters, cameras, and appliances. Actually, there could be more than 139 IoT devices we can use to enable the automation of our home. Interestingly, these devices are always collecting data from the backend. Recently, based on a report from Mozilla to Congress, actually internet service providers are sharing or selling data without users' consent. For example, ISPs are selling real-time location data without meaningful consent. Comcast is manipulating DNS to serve customized advertisements, and Verizon is using super cookies to track users' internet activity. For AT&T users, they have to pay an extra $29 per month if they don't want their internet use data being collected. However, this kind of data sharing is beyond the ISPs. Actually, more parties can have the data, like IoT manufacturers and other third parties. As you can see the examples here, recent research shows that there are 72 out of 81 popular IoT devices are collecting and sharing the data with third parties all the time, including Google, Amazon, and Akamai. And this kind of data sharing is actually not necessary for enhancing customer experience. They are completely unrelated to original manufacturer and far beyond the basic necessary device configuration. Many of these examples are voice speakers, smart TVs, and streaming dongles. A quick example here. If you pair your motion sensor with the Alexa, actually you may be sharing data from motion sensor with multiple parties. Now let's look at what kind of privacy information can be revealed. Here are two graphs of traffic volume data segments. The x-axis is the time and the y-axis is the traffic rate at kb per second. In graph A, we can clearly see the traffic generated by two voice assistants, which are both user interactive, and this will reveal the home's occupancy. In graph B, which is a sleep sensor, we can also see the user's sleep pattern very clearly. These are only basic examples, and actually combining with other resources of information, an adversary can learn many other user behavior information. For example, do the occupants have regular jobs? How often do occupants go out for vacations? How often do occupants eat in versus go out to eat? And what are the occupants' favorite TV shows? So our research problem is, how do we defend against this sort of malicious IoT data analytics to protect the user's privacy with a reasonable cost, while we still want to permit sophisticated data analytics, which is necessary in smart home automation? As shown in the graph here, our adversaries are mainly unpaused adversaries like ISPs, third parties like device manufacturers, or network content providers like Akamai. Currently, there are many researchers propose different privacy-preserving approaches focusing on reshaping the traffic volume data. We have summarized them into three major categories: pure traffic injection, hybrid traffic reshaping, and random traffic padding, shown in graph B, C, and D. We have benchmarked these three different approaches, and as we can see from the table, these approaches have different performance, and they are also showing different traffic overhead. Basically, to better preserve a user privacy, using the existing approaches, we have to spend more traffic overhead. Let me briefly summarize the limitations in this existing work. First, the traffic traces are not smartly reshaped, and the traffic injection is not bidirectional. And the privacy-preserving operations, including flattening, injection, or reshaping, have practical limitations, and there also lacks a trade-off point between additional traffic overhead and user privacy preserving. So to address these limitations, we present a new system called PrivacyGuard, which is a low-cost, open-source, and user-tunable smart home privacy preserving system. Our system significantly reduced the privacy leakage from IoT network traffic data sharing, and we still permit sophisticated data analytics that was necessary in smart home management. This graph shows the pipeline of our system design. Now I will discuss each step in our pipeline. The first step is building adversarial machine learning and deep learning attack model. To build the attacking model, the first step is identifying principal features. We did empirical benchmarking on many statistical metrics and find out 8 most significant and principal features. As shown in the table here, which are 2 traffic flows from Amazon Echo and Baby Monitor, if we use these 8 features here, we can clearly distinguish them. After we figure out the features, the next step is training the attacking model. So what kind of model did we use? We actually benchmarked the machine learning models mentioned in relative works, including decision tree, random forest, support vector machine with different kernels, and logistic regression. Of course, we also consider the most recent deep learning based approaches. The graph on the right shows a pipeline of CNN network. I will not go through the details due to time constraints. After we use these models, the table reports the performance. As we can see here, for these 13 different user activities, using different attacking models, we can perfectly detect all of them. It proves that the attack model is accurate, and we will use these attack models to evaluate our work later. The next step is intelligent traffic rate signature learning. So the first thing is, what is traffic rate signature? Here are 3 examples from Amazon Echo, Google Home, and Dropcam. We consider the spikes as traffic signature, and the signature have 2 directions. We have incoming traffic signature and outgoing traffic signature. When starting PrivacyGuard in a new smart home, it will start learning device traffic signatures automatically and store them in a SQLite database. And we also apply PCC to distinguish duplicated traffic pattern. And we weight all the traffic patterns according to their appearing frequency and the traffic rate to perform a smarter traffic signature injection. And for devices that have not enough traffic signature samples, we also employed DC-GAN to generate more traffic signature sample for the signature learning. The third step is artificial traffic signature injection. To inject the traffic signature more efficiently, as we discussed in the limitations, we modeled a user behavior in the smart home using LSTM. Graph A is the pipeline of LSTM model, and graph B shows the injected traffic against the raw traffic. As we introduced before, we inject bidirectional traffic flows to better mimic user interactive devices. However, a fake remote server may reveal its IP address, which is different from IoT servers. So we applied an open source package generator Ostinato to edit the simulated incoming traffic, so that the IP and MAC address shows a consistency to real IoT servers. The fourth step is user-tunable partial traffic reshaping. As you can see from the algorithm on the right side, first, we find an optimal threshold. There are multiple choices provided to the user, and when we reshape the traffic, we are not only aiming at flattening. In addition, we also consider extension. You can see a very straightforward illustration of our reshaping from graph A. And the final stage is online optimization. Our online optimization are mainly focused on the traffic signature adjustments and also the reshaping rate dynamic adjustments. Here we list the open source frameworks and online services we implemented to develop our PrivacyGuard. Here is an overview of our prototype. The PrivacyGuard is running on a Raspberry Pi 4. We have multiple IoT devices including hubs, voice assistants, cameras, and plugs. All of the devices are connected to a Netgear router flashed with DDWRT system. Here is our evaluation setup. We used 5 different datasets to evaluate 5 different approaches, and also we are using 5 different metrics to quantify the performance of both PrivacyGuard and other works. First, we want to evaluate whether PrivacyGuard is capable of preventing detection of user activity information. The x-axis is 9 different user activities, and the y-axis is the MCC of attacking models on different privacy-preserving approaches. Here we can see that the PrivacyGuard, which is the red and green bars, are reporting worst MCC, which means that it's best approach to preserve user activity. Next, we want to see if the data granularity changes, how will our performance change. X-axis is 5 different time granularities, and the y-axis is the MCC. Precisely, coarser LT traffic will make some features unidentifiable, including standard deviation, variation coefficient, and area under the curve. We have tested 5 different data granularities, and the result shows that PrivacyGuard holds robustness against changes to data granularity. Then, we also quantify the accuracy when user performance changes, the user preference changes. The x-axis of the graph is the additional traffic overheads, and the y-axis is the MCC. And we can see that the PrivacyGuard significantly lowers the MCC of the attacking model at around 100 megabits additional traffic per day, and the user can also increase the traffic overhead further to preserve the privacy. Next, beyond the statistic attackers, we also consider adaptive adversaries attacking our privacy-preserving approaches. The x-axis is the additional traffic, and the y-axis is called adversary confidence. We pick 6 devices that have the highest traffic consumption, and the adversary confidence drops quickly when PrivacyGuard uses more traffic overhead. In particular, the cameras are reporting fastest adversary confidence decreasing. This is mainly due to the fact that these IoT devices have more unstable traffic patterns that allow them to better respond to our PrivacyGuard. In addition, we also consider another interesting part. We evaluate the adaptive adversary based on their knowledge level to our model and ground truth data. The result shows that PrivacyGuard yields an MCC of 0.35, which is almost 2 times less than the original traffic MCC when the adversary is having 100% knowledge of our modeling, which means that PrivacyGuard can defend a perfectly trained model. Here we conclude our work. We propose the PrivacyGuard, which is a new, low-cost, open-source smart home user privacy preserving system. It supports user tunable injecting and reshaping, as well as automatically optimization with trade-off point provided. About the future work, currently we deploy the PrivacyGuard on a Raspberry Pi, and we're working on removing such additional devices from the smart home. We're looking into different directions, including run the PrivacyGuard into an already deployed IoT device, or combine the PrivacyGuard with a smart router operating system. Thank you all for the listening, and you can find all of our source codes and datasets on our GitHub site.